Thanks, Raghuram, for the introduction. So, as the afternoon chairman earlier said today on the occasion of his talk, everybody has to pick a club regarding L functions. So I picked the p-adic L club. So yeah, so that's a L function. And so the way I'll organize this talk will be first explaining kind of an application we have. So everything non-trivial in this talk is based on a joint work with Adele Bettina, and I will first explain some consequences that we draw on the Katz p-adic L function, which has been studied for a while, and then I will go to what's behind the proof and maybe do some digressions in other directions. I have to say that's probably lucky for me. So the field of p-adic L functions has been so far not kind of overshadowed by the Perfectoid development, because I'm not really up to date with those kind of techniques. But so far it's safe to say to stay in this area and do mathematics. So throughout this talk, and maybe also the next talk, K will be an imaginary quadratic field. And P can really be any prime. So if you like P equals 2, you can do this. So P is a prime. But we will assume, however, P to be split, which splits P bar in K. And we will fix once and for all embeddings of Q bar, the field of algebraic numbers, in C. So this determines a CM type. So an isomorphisms of K tensor R with C, and also determines a preferred complex conjugation in the absolute Galois group of Q. So this is complex conjugation. And we will also fix an embedding of Q bar in QP bar, which will specify first the decomposition group. So this embeds GQP with GKP as a decomposition group in GK, and also well, this P is depending on this choice a prime above P. Okay, so right. So given, so I should maybe start here one. So Katz p-adic L. So fix some auxiliary ideal C in OK, prime to P for this talk. And so given, so what Katz has proved, so in his annals paper, so Katz proves that there exists a measure mu C on the maximal abelian extension of K, which is unramified outside P infinity times C, such that for any character phi, of this group, always some, well, I can put QP bar, that's fine, okay. Of infinity type. So this is an algebraic Hecke character of correct infinity type which ensures criticality of the attached representation. So when you evaluate this measure at phi, you have a very precise formula which I can write just to show you how that there is no ambiguity. So there is some factorial, and then so those are, I'll say, periods of a CM elliptic curve which are defined up to some rational number, but which simplifies in this notation because we consider a quotient. And then what we are interested in are those extra factors, which we saw also in the talk earlier this week of Denis Benois. So what happens is when you vary the character, the L function doesn't vary well p-adically. Well, this is clear a posteriori, because if the whole thing varies well p-adically, those things individually don't vary well p-adically. So somehow this explains a posteriori the approach. But anyway, so that's that's Gothic P. I mean, everywhere. Okay. So those are the p-adic. So those are the periods. So those are periods of the elliptic curve C modulo Gothic C bar inverse. I mean some CM lattice. Okay. No. So okay. I was So this is due to Katz. Well, the construction, but to allow non-trivial character, I should mention the Chalit, and also Hida and Tilouine in the anticyclotomic direction have reworked the construction. Anyway, so this is taken from the literature. For example, Bertolini, Darmon use it under that form, right. Okay, so and the C here means like we omit factors, omit Euler factors. Okay, but this was just to so of course the Hecke characters of such an infinite type are Zariski dense. So they're even p-adically dense, so they determine this measure uniquely. So this is just to give a definition, but as you'll see, what will follow later somehow doesn't depend so much on the particular normalization. This is just to show you that this is some kind of universal, well-defined p-adic L function. Okay, so. Okay, so there is the phenomenon of trivial zeros. Well, so it looks like that if phi of p is 1, this should vanish. Well, this does vanish, but it looks like the whole thing should vanish. This is not a proof, however, because so let's maybe put so for phi of finite order, such that phi of p bar is 1, the extra factor at p vanishes. However, this is not a proof that the p-adic L function vanishes. However, k1, k2 equals to 0, 0 does not belong to the interpolation range. So we cannot simply deduce from the definition that that we have a zero. Let me maybe change a little bit notation to make it really look like an analytic function. So consider epsilon p to be the character from the Galois group of Q, quotient to the maximal ZP extension unramified outside P infinity C mod torsion. So this thing is independent of C, so that's an exercise. This is independent of C. So this is what some authors call W Gothic P. So this is the unique ZP extension unramified outside Gothic P. So consider this character. So that's isomorphic to ZP, and you just include this multiplicatively in P star, and put L sub P of phi SP bar, so those are the two variables, to be mu C of phi times epsilon P epsilon P bar SP bar. So this thing is an analytic. It's a two-variable analytic function, p-adic analytic function. And so henceforth, phi will be a finite order, and we will refer to that as to the two-variable Katz p-adic L function attached to phi. So those are the variables along the p and the p bar direction. Okay, so the Katz p-adic Kronecker limit formula. Okay, so the question I raised just earlier was solved by Katz. So what he did is he constructed the following thing. So first he constructed an improved LP. So how can you improve an LP? So this two-variable p-adic L function cannot be factored. But if you restrict to a line where one of these factors is analytic, then obviously you can consider the quotient, which will only be meromorphic. So what Katz did is he showed that there exists factorization as a product of the analytic function. So when you restrict to Sn to 0, so what Katz showed is that this can be written as 1 minus phi inverse epsilon p to the minus s p bar, my p's, times L. So this is the improved p-adic L function. Yes. Okay, so this is analytic. So this is this means improved. Okay, so now from this formula is clear that if you put s equals 0, so from this formula, a corollary of this is that when actually this only exists when phi is not the trivial character, so it's finite order but not trivial. If it's the trivial character, you cannot improve. There is some pole issue. So when phi is non-trivial, but phi of p bar is 1, so it's trivial at p, or at p bar rather, then the Katz p-adic L function at 0, 0 vanishes for trivial reasons. Okay. And he further showed, Katz showed what I refer to as the Kronecker p-adic limit formula, that the improved L function, when evaluated at 0, equals to the following thing. Log u phi. This is a p-adic log where u sub phi is a certain Robert units in OH q bar phi isotypic part. So let me explain. So H here star. So okay, so those are So here H is the fixed field of phi. So q bar fixed by the kernel. This is a finite order character. So this is H. So H is a cyclic extension of K, and it's an exercise actually to see that this is a line, and there is a canonical way to pick up a unit, a global unit, which, using Roberts units, or there is a different construction using Siegel units, and you have a formula. So what I wanted to say is that this thing is always non-zero because of Baker-Brummer. Oh, it's better, yeah, thank you. Global units, but it's a linear combination with coefficients in q bar. So if phi is quadratic, then it's really a unit. But if phi has a higher order, the coefficients are some cyclotomic, some roots of unity. Okay, so from this formula, it looks it looks like So first, well, this proves that we have a trivial zero, and it looks like the trivial zero should be simple because we have factored something which has a simple zero, and this thing doesn't vanish. However, this is not a proof. This is just evidence. So this hints towards what I've seen conjectured in. It's maybe a folklore conjecture, but it was written in a paper by Ghate and Tilouine, actually in a much more general CM field case. So they have conjectured that under the above assumption that phi is trivial here, so that the order at vanishing at okay, so they have conjectured it in the anticyclotomic direction. Yeah, okay, so let me state precisely their conjecture. So on the order of vanishing at s equals 0 of LP phi s minus s is 1. One can conjecture the same thing for the cyclotomic. So this is referred to as the anticyclotomic L function, which will be very important for this talk. This anticyclotomic p-adic L of Katz. And just orally, if you consider the direction SS, this is the cyclotomic, and that's also conjectured that it has a simple zero in that direction. Of course, because of some linear algebra, there is a direction in which there should be a double zero, because every linear form on a two-dimensional vector space has a kernel. But somehow the conjecture is that this fancy line is neither the cyclotomic nor the anticyclotomic line. And we will try to explain why. Okay, so let me state the question, which well, I could have written conjecture, but we weren't bold enough to write conjecture in our paper, basically because we don't have some numerical evidence which will be safer to have. But it's pretty much a conjecture. Dimitrov. So we conjecture that LP of phi, always the same assumption. Phi is non-trivial, Yeah, so, okay, in addition, so assume phi is anticyclotomic. So this means that phi tau is phi inverse. Tau, remember, is the complex conjugation. I mean, tau, that's an internal conjugation, right? I mean, just to make sure everybody understands this. This is like... So it can also be cyclotomic if it's quadratic, but aside from this case, that's kind of disjoint from the cyclotomic world. So what we conjecture is that this thing should be what we call L of 1. So it's a conjecture. SP plus L of phi minus L of 1 SP bar L star P phi 0. So right. So this L of 1 is this is pretty much this log of u phi p-adic log of u phi from there, plus higher order terms. Okay, and now I'll explain this. Okay, so basically both L of 1 and L of phi are some logs of p-adic units. Some p-adic logs of units. And we will see that, so this is just log of a unit, and this will be like a 2x2 determinant of such things. So I'm coming to the definition of those numbers. Okay, so let's say, yeah, L-invariants. So I should say that, well, we have defined these numbers ad hoc. Somehow they came out of the proof, but they can be interpreted as Benois L-invariants. So I'm not like playing with the words. It's really, but it's a little bit subtle. So I'll probably won't get to that point. So, okay, so now, if some of the students were a little bit lost with the p-adic L functions, we are stepping back on our feet. We'll just do some basic algebraic number theory. So we'll try. So what is given? It's a very simple situation. You can kind of, even it's better if you forget all that was before. So you have an imaginary quadratic field K, and you have extension H. So this is, well, dihedral, well, totally imaginary extension of Q, and somehow so phi is a character of the Galois group of H over K in, let's say, Q bar if you want, so you can see it as a p-adic or a complex character, and we want to somehow attach to this phi some characters, some numbers. Sorry, we want to extract some canonically defined numbers, yeah? H is the fixed field of the character. So H is, so phi is a finite order character of K, and H is the fixed field of phi. And so phi is anticyclotomic. So H can be quadratic over K. I don't exclude that case. I only want phi to be non-trivial, but it can be quadratic. So phi square if an equal 1 is allowed. Right. Yeah. Right. Okay. So the first thing is, if you consider so K, there are finitely many units in K, but so therefore, if you consider the P units, this is if you ignore the torsion, is a rank 1 module. Yeah.
So if you allow the square equals 1,
yeah.
this is not Perfectoid.
Well, depends where the Klein group is dihedral or not. I mean, for some people it is. Isn't it? I think it's dihedral for most, like from the perspective of, yeah, like Galois representations, we don't want to treat it separately. Okay, right, so you choose an element here such that the ideal generated by this, it's p to the class number, so this determines this uniquely. And so you define L of 1. Actually, we kind of, you actually said something stupid, I guess. Maybe just erase this. Yeah, it's a little bit, erase this, please, yeah. Okay, so L of 1, no, there was some confusion, yeah. This is the product of, yeah, two things. So L of 1 is log p of up over hk. I mean, you could have taken any element and you should have divided by the ORD p. So I just made that choice. Okay. So that's it's a very easy. So this number is really a classical thing that's used when, for example, one studies elliptic curves with Cm by k. And then you consider u phi, so u phi I already defined, it's there. Okay. And you define the slope. So the slope of phi is defined as S of phi, which is minus log p of this u phi over log p of tau u phi. So as I said, so this thing is a line. So u phi is only defined up to a multiple, but if you do this quotient, this disappears. If you replace u phi by u phi squared, this will remove the ambiguity. And so this slope actually either it's -1 if phi is quadratic, because then it's fixed by tau. So if phi square is 1, or it is not in Q bar by Baker-Brummer otherwise. So basically, if these two global units are not equal, then they're algebraically independent over Q. Okay, so that's the slope. That's easy, relatively. And now I come to the main thing. So the L invariant. So this thing I should explain. So the L invariant of phi is defined as log p of up phi. This I should say what it is. So it's a p unit, you'll see in a second, minus the slope times log p tau of up phi over the ORD p of up phi, where up phi is a p unit. Up phi is in OH 1 over Gothic p units tensor Q bar phi part. So what you can check is, of course, this is a rank 2 module because this module also contains the units. But if you change up phi by a unit, because of the definition of the slope, this will make 0 on the upper floor, so it won't show up. So basically, this only depends on the quotient of this modulo the same thing without, it only depends on the image of this p unit in the p units modulo the units, which is a line. And then I divide by the ord. So this is really independent of all choices. Huh? So both these things, the slope and this thing, they're independent of choice of basis. Okay, so those are like some numbers, and we conjecture that those very kind of natural algebraically number theoretic numbers are the one that occur in the derivative of the p-adic function of Katz. Okay, so are there any questions on the definitions of those numbers, for example? Okay, so if not, so let me write a theorem of what we can prove about this question that we raised. So the theorem that we can prove is the following. So there is a big one, which is that if what we call the anticyclotomic L-invariant, which is just defined as the L-invariant minus 2 times the L of 1. Basically, if you plug S equals, I mean, if you plug here minus SS, then you precisely find L of phi minus 2 L of 1 as a. So if this thing is non-zero, then the anticyclotomic Katz p-adic function, so d over ds of LP phi s minus s is non-zero. So if this magical number is non-zero, then the Katz p-adic function has a simple zero in the anticyclotomic direction, in accordance with the question there. And second, we show that this holds for at least half the characters. So we show that for any phi as above, so anticyclotomic non-trivial, trivial at p, either L phi, either L minus phi or L minus a phi inverse is non-zero. So for example, if phi is quadratic, we know that it's non-zero because that's twice the same number. So that's why I'm saying that one holds for strictly more than half of the characters. And of course, if you assume Chanuel, or actually if you assume something much less stronger than Chanuel, so there is a comment, which is also kind of all I will say about the proof of 2, is that 2 follows from what's called the strong 6 exponential theorem in transcendental number theory. And if what's conjectured, the 4 exponential theorem were true, then both will be non-zero. So both numbers, both L's will be non-zero under the 4 exponential theorem. So the 4 exponential theorem basically says that if you consider a 2 by 2 matrix whose entry are logs of algebraic numbers, if the lines and the columns are linearly independent over Q, so if the determinant is non-zero for some trivial reason, then the determinant is non-zero. Yeah, so if the lines and columns are non-proportional over Q, then they are no proportional over like QP bar.
p-adically, not formally follow complex theory, right? You have to do so.
Yeah, but
Like Baker, yeah.
sure, but for example, so Damien Roy, who showed that theorem, so he first shows the complex, then did the p-adic. I mean, I don't know examples where the complex been done and not the p-adic. I mean,
like Lindemann Weierstrass complex is known, but p-adic.
Right. Okay. Well, I just claimed this. I haven't checked. I mean, Waldschmidt told me this, that for him it's more or less clear that if somebody finds a complex proof, probably it will be possible to adapt unless, yeah. Okay, maybe I should move on. Okay. Okay, so that's what I have to say about the Katz p-adic L function, and now I'll kind of go a little bit in the proof, and actually the proof actually is a corollary of another theorem which will allow me to move to the eigenvariety, which was mentioned yesterday by Sharon Lagdeo. So okay, so yeah, so maybe let me just mention what's the bridge. So the bridge. So okay, I made a comment about 2. So the comment about 1. So the idea of proof of 1 is based actually on the work of Ghate and Tilouine. So Ghate and Tilouine showed that the anticyclotomic p-adic L function. So let me write it as a zeta element. So zeta, yeah, zeta phi minus. So this is each time you have an analytic function which is bounded. So this defines a measure on ZP, and by inverse Mellin transform, this corresponds to an element in all double bracket X, the Iwasawa algebra. So Tilouine and Ghate showed that this thing, so that the element we want to show that, okay, so having a simple 0 at S equals 0 means that X divides this, but X squared does not divide this, right? So Tilouine showed that this thing divides, the characteristic series of a congruence ideal, of the congruence ideal, of the congruence or fusion or C0, goes by many names. Ribet calls it fusion. The congruence ideal between the Ghate theta family, the theta CM family, the Ghate CM family, which I call like big theta phi. So each time you have an anticyclotomic character, you can attach a Hecke character whose transfer for U1 to GL1 is this anticyclotomic character. I should put psi here, yeah, okay. I'll explain what psi. Between this and other families. The congruence, the characteristic series, I should call this, yeah, okay. C0 of psi, something like this. Okay, and actually what we do is we compute, this will be the next result I will present. We compute precisely this congruence ideal. So if it has a simple 0, then anything that divides it is forced to have a simple 0 as well. Okay, so here there is a exercise in class field theory. If any finite order anticyclotomic character can be written, every anticyclotomic finite order character can be written as psi over psi tau. So that's a well-known exercise in people use for transfer between unitary group and GLN, for example. But for GL1, it's an exercise in class field theory. So basically, you have a phi, you have an ambiguity of psi, but you pick any psi like this, and you consider the theta series induction from K to Q of psi, and there is a Hida family going through that thing, and there is a congruence ideal between that family and other families, and yeah, so it's a long proof that they use some Rankin-Selberg, and it's pretty involved. I should say that actually they show this with some assumptions integrally and without assumptions non-integrally. So we only need this. We only need the non-integral version because we care about the zeros at x equals 0. We don't care about the mu invariant in this thing. So it's unconditional. That's why you can allow p equals 2 and things like this. Okay, so let me now go to the main theorem. Okay, and I guess I won't probably say much about the proof. So the main theorem is as follows. So let f be the p-stabilization of the weight 1 theta series which is induction from K to Q of psi. We have assumed that phi of p is 1, and this is equivalent that psi of p is equal to psi of p bar. So this is what yesterday was called alpha p and beta p. So those are, for a theta series, those are the root of the Hecke polynomial. And so we are, this means, so this is the running assumption here on phi. And also a running assumption is that phi is not the trivial character. Therefore, psi is different from psi bar. And this means that this is a cusp form. So this is f is a cusp form. Okay. And in yesterday's language, because those are equal, this means that f is irregular at p. So we are in that kind of a complicated situation on the on the eigenvariety. So consider let t, some kind of a t respectively lambda be the strict initializations of the local rings of the eigencurve respectively of the weight space at f respectively at its weight, which is 1. So lambda, so this is the strict cancellation of the usual lambda. So lambda here is qp bar double bracket x, because you only care about the geometry. So we have inverted p and completed cancellized. Okay. Well, then the theorem is that, okay, let me write it. There are three cases. So as a lambda algebra, so T by standard heated theory is a finite lambda algebra, flat over lambda. You don't speak loud.
The initialization is taken at the point F.
Right. Just because I put QP bar, I didn't just complete, but I also went to something algebraically closed. So, okay. So T, it's either lambda cross lambda cross lambda cross lambda over QP bar. So, so this is the conjecturally only case. So this is if the L invariants, if L minus phi is and L minus phi inverse are both non-zero, and their sum doesn't add up to 0. Or it's lambda QP lambda bracket z square minus lambda square lambda x lambda if the product is 0. Or last case is thanks. What the hell I did here? Z square minus x to the r. I should maybe put some parentheses. That's a fiber product over lambda x to the r minus 1. Sorry. It's okay. Maybe I could have skipped this, but I just want to show that one can really, I mean, determine the Hida family is going through that point. Okay, so this is if the sum is 0. So because both L invariants cannot be simultaneously 0, if one is 0, the other one is non-zero, and then the sum is non-zero. Somehow, yeah, the three bad cases are disjoint. So this is like for some, this is for some E bigger and equals to 2. This is for some R bigger and equal to 3. And this is somehow the first case is the conjecturally only case. So E is supposed to be 1 and R is supposed to be 2. So if you put R equal 2 in the second case or equals 1 in the third case, you fall in the first case. So yeah. Okay, so okay, so this is the theorem. Let me draw a picture maybe, and probably I won't say much about the proof. The proof of this theorem is by deformation theory. It's quite complicated. So what's happening is that the rho f. So let me just say like half a line about the proof. So rho f, which is the induction from K to Q of C, that's a irreducible two-dimensional dihedral representation. So it has a universal deformation ring, but it's kind of hard to study. So what we do is we restrict this to GK, and then it becomes sum of two characters. But then it's hard again because, first of all, to deform reducible representations, one usually uses pseudo-deformations, which is already kind of hard in itself, but then we have to impose an ordinary condition, and that gets even harder because the two characters are equal on the decomposition group. So it's kind of very hard to impose an ordinary condition. Yeah, so the R univ of rho f is fine, but the R kind of ord rho f is not well defined in Mazur sense because you don't have a line to pick up. So what we do is instead we study deformations of these guys, rho and rho prime. So we pick up a non-trivial extension in one direction and in the other. But then the problem is that eta and eta prime have infinite order. So we have lost the advantage of having something with finite image. But it's still better because these have a universal ordinary deformation rings in the sense of Mazur, those guys, because not only the centralizer is trivial here, but also there is a unique ordinary line because this thing is ramified at P. So this leads to R rho ord and R rho prime ord. And somehow from both we concoct something which we call our perp rho. And this R perp rho actually will be modular and will correspond to all the non-CM families. So the picture we end up with is that we have this point F on the, so this is the drawing on the eigenvariety, so E, which is over the weight space. So at F, there are 4 families. So there is one family, which is a theta family, which is induced from K to Q. So this is the theta psi. So Galois-theoretically, this is just you induce psi times universal p ramified character. So this p, yeah, erased. So this is the character that corresponds to the maximal ZP extension that I earlier mentioned, unramified outside Gothic P. Then you have another family, which is theta psi bar, because psi and psi bar are different, but they're locally the same at P. So both those give P ordinary deformation. So those are two CM families by K. And what the theorem says is that in addition, you have 2 more families. So you have another family, which I call F. And there is necessarily F tensor, the quadratic character family. So these 2 families, if the product of the L-invariants is 0, actually they're the same family. That's not supposed to happen, but it could be, we don't know. So there are 3 or 4 families. This can end up be the same family. But that's basically the picture. And I want to say is that in the quadratic case, it's interesting because those families are also CM, but by a different field. So there is a particular case. So when phi is quadratic, then H is big quadratic. H is K prime for 2 imaginary quadratic fields. And both these families F and F tensor epsilon K have CM by K prime. So there are 4 families which have CM but 2 by 2 by different fields that go through that point. Yeah, so I want to say something here. So one of the actors who pulled me in this kind of mathematics is Eknath, who's present here. So a while ago, we were looking for points on the eigencurve where non-smooth weight 1 points. And so basically, we gave this example of this biquadratic thing. So 2 families having CM by K and 2 CM by K prime. But Eknath, somehow his first idea, which he had even before he met me, was that the simplest example, so Eknath thought that that the simplest example, so there should exist CM weight 1 forms which belong to a non-CM family, because we already have by Hida theory the CM family, so if there were a non-CM family, that would be the most obvious example of a non-regular point. But we after spending like a couple of months on Magma and Paris and all kinds of softwares, we couldn't come up with a conclusive example. And it's funny that after those years, it turns out that not only there are such examples, but all examples are like this. So what's a corollary of what we did is that actually, if you consider any, what we consider that actually any CM weight 1 form, which is irregular at P, and that's a necessary assumption by the result I have with Bellaish, because the regular ones will belong to a unique family. So any weight 1 form which is irregular at P belongs to a non-CM Hida family. And I even prepared an example. Maybe this will be my closing. It's kind of nice. I found it in a relatively recent paper of Serre, 2003. So, I mean, it's a well-known example, but I found it like with all the details. So if you consider K to be Q of square root of minus 23, so this is the smallest number field having smallest discriminant number field having class number 3. So you consider H is the Hilbert field, so this is the splitting field of the polynomial x3 minus x minus 1. And you can also write it as Q adjoint third root of 3 plus square root of minus 23 over 2. And so you can ask the question, which are the primes for which this polynomial has roots in Fp? So P splits totally in H. So first it has to split in K, so you need minus 23 over P to be 1, which by Gauss reciprocity is P over 23. So this is a congruence condition mod 23. But the other condition is that P should be writable as a ternary quadratic form like this. And because of the class number, this is known that doesn't correspond to a congruence condition and actually corresponds exactly to, actually this condition here is non-congruence. So this was the point Serre was giving as an example. And actually that condition is equivalent to AP being 2, where, so what's AP? Where actually you consider the unique weight 1 form of level 23, so that's theta series. You write it as sum of A and Q to the n, and at least 1. And actually it also has expression as a eta function, or it can be rewritten beautifully like this. So those numbers are really easy to compute. And so the smallest example of irregular prime, so this in our language means theta to be irregular at P. And the smallest such P, it's easy to find with this representation, is 59. So I guess that's maybe, the easiest example of a singular point on the eigenvariety. And I want, maybe as a closing remark, I won't write anything. I just say that yesterday Shaunak said that we are interested in proving that the eigencurve is smooth at weight 1 points because maybe we want to construct p-adic functions or show some other things. And actually, this was also my original motivation, but since then, it turns out that the points where the weight one points where the eigencurve is not smooth are even more interesting because, for example, there are what's called overconvergent Weightman modular forms at such points, and their coefficients are related by Darmon, Lauder, Roger to the Kudla program. So, and also by Belishin-Ivier, when there is some singularity in eigenvarieties believed, one can construct non-trivial elements in Selmer groups. So I hope that the non-triviality of this point will be a nice thing to explore further. Thank you.